This week, we will continue our discussion of Box Jenkins models. We will focus on non-stationary series and forecasting. Up to this point, we have only discussed stationary time series in regards to BJ modeling. We know that sometimes series do not have a stable mean, variance, or both. In particular, we will discuss how to model series with constant variation, yet an unstable mean. Here, we will employ the differencing technique to stabilize the series. This type of BJ modeling is called autoregressive integrated moving average or ARIMA PDQ modeling. Notice that this is similar to the stationary case, except now we include the term integrated to account for the non-stationary property. You should also notice that there is an extra letter in the parentheses. The letter D stands for the degree of differencing used to create a stationary series. Usually for the non-seasonal cases, we shouldn't need differencing beyond the first or second order to alleviate the non-stationarity. Once we get a stationary series, we decide on the values for P and Q in the same manner as we did in the previous lecture. Recall the Dow Jones data from a previous lecture. Here is the series plotted over time. You should be able to see that it has a valley at about 2003. Did we consider this stationary? To remind us, let's take a look at the ACF plot. Notice that the estimates for the ACF yield large values even at large lags. What should you conclude here? Based on both plots, we would decide that the process is not stationary. One thing that we can do is try the first differences. Here is the ACF plot for the first differences. Did the differencing take care of the problem? Based on the plot, we can conclude that the first differences are indeed a stationary series. Let's take a look at some plots of certain ARIMA models. The models that will be simulated are given on the slide. Each model will use the same value for the parameters. Here is the plot of the simulated series from our ARIMA 011 model. Let's look at the ACF plot. Would you consider this stationary? Here is the plot of the series after the first differencing. Does it now seem stationary? Here is the ACF plot. You should not be surprised that the sample ACF at lag 1 is large. Why is this? Here is the ARIMA 110 series plotted over time. Here is the ACF plot. Notice that once again the sample ACF values are large for large lags. This shouldn't be surprising based on the model that the data was simulated from. Now let's take the first differences. Here is the plot of the first differences. It seems like the process is more stable. What do you expect the ACF plot to look like? Notice the alternating pattern on the sample ACF values for this plot. We expect this behavior from the ACF plot since P greater than 0. Finally, here is the ARIMA 111 series. This plot would not lead us to conclude that the series is stationary. To get another view, let's look at the sample ACF plot. In this plot, we can see both types of behavior. But again, the sample ACF values at large lags is large, indicating that the series is not stationary. Let's try the first differences. The series created from the first differences seems stationary. Now, based on the model that this data was simulated from, what do you expect the ACF plot to look like? Here is the ACF plot. It does seem to exhibit that oscillating sign decay pattern. Now that we have seen what some ARIMA PDQ models look like, let's talk about model building. It is a three-step iterative process. First, we determine an initial model. Now estimate the parameters for that model. Finally, we use diagnostic checks to assess the model adequacy. At this point, we are concerned with model identification, not forecasting. So we are judging the model first based on adequacy. We will judge them based on forecasting later. The first step in model identification is to assess stationarity. If the series is not stationary, then we need to make it stationary. Once we determine a stationary series, we will use the sample ACF and PACF plots to determine the orders for the autoregressive and moving average components. At this point, we may have multiple models. Once we determine if these models are adequate, we would use fit statistics to decide which model is best. We should also not forget about parsimony. Let's use the BJ techniques to fit models for the simulated ARIMA 111 series that we created previously. Although we are not doing it, you should be able to determine what the sample ACF and PACF plots would like for the other series as well. Here is the ACF plot for the difference ARIMA 111 series. Based on this, it doesn't seem to cut off. This would indicate that the behavior could be MA only or ARMA based on the sample PACF plot. Here is the sample PACF plot. There doesn't seem to be any cutoff point in a small number of lags here as well. This would indicate that the behavior could be ARIMA 111, which is what we would expect. Notice that in either plot, I didn't try to count the number of lags until it cut off. We don't do that for this type of series. In other words, you should be typically fitting order 1 for both of these. Here are the results of the model. Notice that the printout includes the call from the R software. Here it gives the estimates for the coefficients and their standard errors. You can see for both parameters the coefficients are small as compared to their standard errors. Also in bold is the estimate of sigma square and the AIC. We would utilize these if we wanted to compare this model with other candidate models. Let's look at the diagnostic plots. Here are the diagnostic plots as given by the R software. We can see that we do have some standardized residuals that are extreme, close to 3 in absolute value. The p-values and the ACF plot show no issues. Now let's look at an example where a chemical company would like to develop a model and forecasts for daily viscosity readings. Here is the series. From this plot, the series seems to be stationary. Let's look at the ACF plot to verify. Here is the sample ACF plot. The sample ACF plot seems to exhibit die down after a small number of lags. From the plots, it seems that the series is stationary. Now let's look again at the sample ACF and also the sample PACF plot to decide on some candidate models. Here is the ACF plot. Notice that I have reduced the range of the y-axis to give us a better idea of what is going on. You should see that the die-down behavior is even more apparent here. Now let's look at the sample PACF plot. From this, it seems that we have large sample PACF values up until lag 2. You could also argue that lag 3 is somewhat large as well. Some mid-analysis conclusions are that the ACF dies down and the PACF seems to cut off after either lag 2 or 3. So we have two competing models. These are ARIMA 200 or ARIMA 300. You could also look at these as AR2 or AR3. We will keep everything general, so we will use the ARIMA term. Here are the results of both model fits. For the ARIMA 200 model, the standard errors of the estimates are small as compared to the estimates themselves. For the ARIMA 300, the standard error for the estimated phi3 is 50% of the estimate. This indicates that we should be somewhat suspect of the need for this parameter. Now, to compare the models, we use the AIC criteria. You can see that the AIC for the ARIMA 300 model is smaller. This indicates that the ARIMA 300 model is a better fit. We see the same relationship when we look at the estimated model variance. Based on this, we should choose the ARIMA 300 model. Now let's look at the diagnostic checks. Based on the diagnostic plots, it seems that we do have an extreme standardized residual beyond -3. Other than that, things look fine. So to conclude from this example, we should fit the ARIMA 300 model. But what about prediction intervals? For the ARIMA PDD model, tau step ahead forecast is given in the slide. This leads to the tau step ahead forecast error. Notice that this really is no different than the forecast errors from the previous techniques, except how we get the forecast itself. Note that the forecast errors are just linear combinations of random shocks, so they have mean 0 and variance sigma square of tau. Now notice how we get the variance. What property needs to be true in order for this variance calculation to be valid? Something to note is that we expect the variance of a forecast to increase with the forecast lead time. This should be apparent since we expect more uncertainty as we move away from the last time period used to create the model. The distribution of the forecast errors is normal with mean 0 and variance as seen on the previous slide. This holds only if we assume that the random shocks follow the typical assumptions. The prediction intervals are given in the slide. Let's go back to the viscosity example and determine the piece for the next month. Here are the fits and 95% piece. Now let's plot them and compare with the data. Here is the plot of the fits, forecasts, and PIs. Next time, we will conclude our discussion on BJ techniques by discussing seasonal models.